Alright, welcome everyone to this video. We're going to continue our discussion of two-component phase diagrams. So in the previous video, we showed what the pressure versus mole fraction in the liquid phase or mole fraction in the gas phase come out to be. If we plot both of these things on the same plot, right, where now the x-axis is going to be the total mole fraction, okay? And for that, we're going to use Z of A. So it's going to be the moles of A in both phases divided by the total number of moles in both phases, right? And so, again, X of A is only moles that exist in the liquid phase. Y of A is moles that exist in the vapor phase, okay? Right? And so again, there's not just necessarily the liquid phase or the gas phase, and there's not necessarily just a single line that appears in these phase diagrams, right? And so let's talk about what this phase diagram tells us, what's going on in this phase diagram. Okay? So let's consider a system where I'm going to keep myself at constant total composition, okay? Which means, right, I'm not adding or subtracting moles from this system, right? I'm potentially just changing what phase the moles are in, right? So we're going to start at point A on this plot at a very high pressure, and we're going to slowly decrease the pressure in the system and talk about what happens, right? So at the very beginning, at point A, where the pressure of A is greater than the pressure represented that first line, okay? Right? Then we basically just have all of our moles in the liquid phase, right? And so the total mole fraction, Z of A, just equals the mole fraction in the liquid phase, right? Because I have essentially everything in the liquid phase, right? Okay. If there's some amount of vapor, things like that, right? It's a very minuscule amount, right? That there are some, right? Every liquid has some vapor above it, right? But the total number of moles in the vapor phase compared to the liquid phase is minuscule, and so we consider, right, the mole fraction to be just the mole fraction of the liquid phase, okay? Right? And at this point, right, we're at a system where there's only one thing in equilibrium, right? And I can vary either my composition or my pressure and still maintain just being in the liquid phase, right? Again, this is assuming a constant temperature process. Okay, that's why we only have 2 degrees of freedom, right? It's because we're assuming we're doing this isothermally. Now, if we lower that pressure, right, until the pressure equals the pressure labeled P1 here, which is at point A1 in this phase diagram, okay, right? At this point, okay, right, we have essentially these two different phases, right? We have the pure vapor phase, okay? Pure vapor phase is the bottom here, right? And pure liquid phase is at the top of this, right? Okay. At point A here, okay, at point A1, right, the composition of the vapor phase is going to be represented by the composition at that pressure for that phase boundary, okay? So I just draw a horizontal line connecting the top phase boundary with the bottom phase boundary, okay? And this tells me, right, that my chemical composition, okay, in the liquid phase, and this tells me the chemical composition in the gas phase, okay? Right, draw a straight line down to the x-axis, okay? And that's how you get the chemical composition of the gas phase, right? And you notice that they are different, right? The liquid phase and the gas phase, right? And at point A1, right, we're still basically, everything's in the liquid phase, right? But now we're starting to generate some gas, right? As I'm lowering this pressure, okay? And so, right, A1, you can still consider that since there's minimal vapor, right? That we can still consider this to have the total composition is basically the composition in the liquid phase, right? Z of A equals X of A, okay? Right, now, in this case, right, I have two phases that are now in equilibrium. I have the liquid phase and the vapor phase that are in equilibrium, right, because I now have some amount of vapor, okay, in which case now I only have 1 degree of freedom, right. If I change the pressure, I got to change the chemical composition, right, or vice versa. Right, now if I continue to lower things, right, lower my pressure in my system to, say, the point where I'm at P2, which gives me point A2 here on this diagram, right, well now I'm in this middle region here, okay, where this middle region represents a equilibrium between the liquid and vapor phase, right? So this equilibrium is no longer just a straight line, right? So in a single component phase diagram, right, the equilibrium between the liquid and vapor phase is a line. In a two component phase diagram, that equilibrium is a surface, is a plane, right? It's not just a straight line. So within this region here, I have both the liquid and vapor phase in equilibrium with each other, okay? And so they're in equilibrium. I'm at point A2, okay? The composition of the liquid phase at this pressure is given by the point here, right? And I draw that down, okay? Composition of the vapor phase is given by point A2 prime, okay? I draw that down, right? And that gives me YA, and again over here gives me XA, right? So I see, right, that the composition in the liquid phase and the vapor phase is changing, right, as I change the total pressure, which is what we should expect, okay? But again, like a single component phase diagram, right, I can use kind of the relationship between pressure. In single components, we had a relationship between pressure and temperature. Here, we have a relationship between pressure and chemical composition that gives us an idea, right, of where these boundaries are, and the compositions, right, are related to where these vapor pressure boundaries are and these phase boundaries are, okay? So if I continue lowering my pressure until I get to A3, okay, prime here, right, now, okay, at this point, right, now my Y of A, right, my composition in the vapor phase is now representing the majority of my moles, right? Now I got most things in the liquid phase, right? I started off, or in the vapor phase, right? I started off everything in the liquid phase up here, right? Okay, start off in the liquid phase, okay, up here. I get to this point, A1, right? I still got basically almost everything in the liquid phase, right? Well, now in this intermediate region, I have a mixture of liquid plus vapor, okay? And then once I get to point A3, I've now basically boiled off, right, all of my liquid, and I now just have the vapor left, okay, at A3 prime. And so YA, right, is going to be equal to ZA, the total composition, okay. And at A3 prime, right, the composition of the liquid is A3, right. This point here gives us the chemical composition of the liquid, right. Then once I lower the pressure past that, right, I'm just now changing the pressure in the vapor phase, and I just have the vapor phase in equilibrium. I don't have two phases in equilibrium now, just the one. I can vary these things however I want, okay? Right, and so again, summary of this, right, this two-component phase diagram, right, we have, right, liquid and vapor phases that exist here, and then we have a point where the two phases are in equilibrium, but it's no longer just a line, but it's now this chunk, this surface, right, that has two phases in equilibrium, okay? Otherwise, it's very similar to things we've talked about with single component phase diagrams. And so one quick note when talking about the relative amounts of liquid versus vapor, okay, you can get that by this lever rule, okay. If you have the phase diagram, okay, and you just on the diagram itself measure the distance from the point you're at to the liquid phase and the point you're at to the vapor phase, right, to get these length A and length B terms, or alpha beta terms here, right? The length of alpha, length of beta is just literally that distance, right, in this plot, okay? So, right, it's a difference in, right, if the total composition of your system is like 0.7 and alpha is 0.6, and n beta is 0.9 or something like that, right? Then it would be like 0.1 and 0.2, okay, right? So again, it's a difference in the compositions, okay, of the total composition, the vapor composition, and the liquid composition, right? So if you have those differences, okay, then you can relate the total number of moles in alpha phase with the total number of moles on the beta phase, given this equation here, where the number of moles in the alpha phase times that distance, that L alpha, has to equal the number of moles on the beta phase times the distance L beta. Okay, where again these distances, right, are sort of the intersections of these curves, right? Which again you could calculate if you know the total composition and you know enough information, right, to get the vapor, with the composition in the liquid phase and the composition in the vapor phase, right? You can calculate those distances using that information as well. Okay, and that does it for this video, at least on two-component phase diagrams.